Alright, hi y'all. Today we're going to be doing a TDR problem, a time domain reflectometer type of problem here. This was on, I believe, Blast from the Past, but it was on a final exam, problem 1. As you can see, it's 20 points, so it's not that many points, but it's a candidate for being on, our first exam. Although this type of problem has never been on our first exam. Alright, so let's read the problem. So a TDR is being used to determine a fault on a transmission line. The TDR has a voltage generator VG of T that applies a voltage step function with an amplitude of 2 volts. Okay, so let's write that here. What that looks like is we have an amplitude of 2 and a unit step function, right? So 2U of T, that's our VG of T. That's what this is equal to. The transmission line has a relative permittivity, epsilon R is equal to 2.1, and the voltage waveform V0 of T that is recorded by the TDR at Z is equal to 0, so this is where a TDR is, right, is shown below. So this is what the TDR records, or record here, is what it records. A partial short on the line, so partial short on the line, the fault is modeled as a parallel resistance, which is right here. So now we have to determine the unknown resistance RP and the distance between the short and the TDR. It says support your answer by constructing a bounce diagram and using it to get the voltage V0 of T in terms of D and RP. Okay, so the first thing that I would like to do is write down some equations we know. So we know there is a time delay, or T jump, at 0.290 microseconds. 0.290 microseconds. Well, in the notes for, I believe it's at the very end of notes 8 in bounce diagrams, it tells us whenever we use a reflectometer, time domain reflectometer, the time delay is also equal to 2 times the distance of the fault from, your source divided by the speed of light in the dielectric. Well, this is what we're looking for, ZF, and we have TD. But what is CD? Well, this should be a common equation we should know. This should be on your crib sheet for sure. CD is equal to the speed of light divided by the square root of the relative permittivity. And we can solve for this very easily. We can then say the time delay is equal to 2ZF times the square root of epsilon R divided by C, just using some algebra. And now we want to solve for ZF. The distance is equal to C times TD over 2 square root of epsilon R. So now if we plug in our numbers, we get 3 times 10 to the 8th times the time delay, 0.290 times 10 to the negative 6th, divided by 2 times the square root of 2.1. And what we get is we get the distance from the short to the TDR is about 30.02 meters. 30.02 meters, not 30.2. 30.02 meters. Okay. So that's our distance, that's our D, and that would be one of the parts. Now, to solve for the unknown resistance, it says to support your answer by constructing a bounce diagram. Okay. Well, it might be easiest to use this here to construct a bounce diagram. Well, why is that? Well, this V out of T is the recorded value of the voltage as a function of time, at a specific length. L is equal to 0, or Z is equal to 0. So it's actually very easy to create a bounce diagram from this. Now, how is that? Well, if we notice, this is the incident wave, V plus, because you have a unit step function. Remember, what is V plus equal to? V plus, the incident wave, is equal to V naught, your amplitude of the source, times Z naught over RG plus Z naught. I believe it should be. But then what you get here is 2 times 1 over 2, because you have 50 over 50 plus 50 is 100. And then you get 1 volt. So that's how they get this 1 volt. Now, at some time here, the time here, drops. But why does it drop? Well, let's look at our circuit here. Is there any reflections going on? Is there a reflection here? No, not exactly. There's not a reflection at the source because the impedances are matching. Is there a reflection at the load? No, there's not a reflection at the load. So where must there be a reflection? Well, there has to be a reflection here between this parallel resistance and this characteristic impedance. There has to be. Because how else would the voltage drop? What that means is there must be a negative voltage being applied from the junction back to our source at z is equal to 0. But what is that? Well, it is the difference 0.286, 1 minus 0.286, because you have to have, 1, because this should have been 1 the whole time, but it dropped by how much? What is the distance? 1 minus 0.286, 0.714. And what direction is it going in? It's negative. Of course, you're subtracting, so you should get a negative here. All right. So that is our value that it's coming back at. There has to be, the reflection has to be that. Reflection caused by the reflection caused by this fault resistor has to be negative 0.714. Now, let's do a bounce diagram because that might make more sense. Instead of analytically solving this graph, let's create a bounce diagram. Okay, so how are we going to create this bounce diagram? Well, let's first start off with the time, okay? So t is equal to 0 up here. Now, what else do we have? We have some time t it takes to get down the line, right? So what we can say is this is t, and this is t. Okay, so then it takes t time, so 2t, 3t, and 4t. Why can we say that these t's are the same? If you want to think about it, you can, definitely do. So the reason we can say these t values, these periods, are the same is because we have the same epsilon r. Also, we have the same intrinsic, or I guess characteristic impedance. Not intrinsic, I don't know what the hell is going with that. But remember, the speed of light down the transmission line will always be the speed of light divided by the relative permittivity, the square root of it. So that means the period it takes will be the same. Okay, hopefully that makes sense. But what else do you need to know about, a bounce diagram? Well, you need to know the reflection coefficient at the source, and you need to know the reflection coefficient at the load. In our case, it would be the junction. Why not the load, though? Isn't there some load here? Well, what do you notice? There's going to be no reflection at the load, so we don't really have to worry about it. If we wanted to worry about it, what we could do is we could, split this in half, but, you have gamma L is equal to 0, because there's no mismatching in the impedance. So that really doesn't matter. You don't have to put that. So we have to have the gamma G and the gamma J. Okay, well, what is gamma G? Well, do the impedances match? Yeah, they do. So we can keep this as 0. Okay. Now, what is gamma J? Gamma J is difficult. The reason being is because we don't know this until we know that fault resistor. So what can we do then? Well, let's finish out our bounce diagram here. How long does it take to get from the source to the junction? Well, it takes t time. So what we're going to do is we're going to create a line here that takes t time, and then it takes t time to get back. And then it takes t time to go there, and then there. So we have our values here, and we always know to the right of the first line is 0. And to the left line, well, what is that? Well, we don't really know what that is. We know it's going to be V plus. Now, what was V plus? This is 1 volt. Okay, well, what about this value here? If you remember from, whenever we first went over bounce diagrams in Unit 8, or Notes 8, the value on the line was, your gamma L, or in our case, J, times V plus, because once it hits this bounce, once it bounces off the wall, we have to multiply by the gamma J. But now what we have is in this triangle, we have gamma J plus 1 times V plus. Okay, so this is the voltage in that area, and that's what we want to use. Well, why do we want to use that? Because we know the voltage after after it hits the junction. We know the voltage. That voltage is 0.286. Okay. So what we can do then is solve for gamma J, because we know 0.286 is supposed to be in here because it's the voltage after it hits the junction, and is equal to gamma J plus 1 times V plus, which is 1. So what do we get? 0.286 is equal to, divided by 1, gamma J plus 1, and gamma J is equal to negative 0.714. Well, what do you know? This value here is the same as this value here. So there's one way you could do it, and it's quick, but it is a little more advanced because you don't do all the steps for the bounce diagram. And you have to understand how the bounces and the reflections work. For this way, it's clear cut, shows all the work you need, and of course you would have to do it for this one because it says support your answer by constructing a bounce diagram. But now we have gamma J. Well, what's so important about gamma J? Well, gamma J is going to be equal to what? It's going to be equal to the resistance, or I guess we can put impedance, as seen from the source, or as seen from this source. So we have Z as seen from the source, and I'll put Z L for Z load, right? It sees the fault resistor and load. ZL, what is it? It's minus your initial Z naught divided by ZL plus Z naught. This is the equation for, a reflection coefficient. ZL is the impedance as seen by our source. So what we see is this value and this value. But why are we doing it as seen by the source? Well, if you remember from the very beginning, this here is where's the TDR? The TDR is here. So what we have to do is everything has to be as seen by the source, because that's where the TDR is. Okay, so what we get is, what is ZL? Well, ZL is, you have your two parallel resistors. So you have 50 times RP divided by 50 plus RP minus the characteristic impedance minus 50 divided by ZL, which is 50 RP again, divided by 50 plus RP plus 50. And this is equal to gamma J, which is negative 0.714. Doing some algebra here. I guess I do have a little bit of time. I can show y'all like quick steps to do this. I'm not going to actually solve it, but you multiply by 50 RP divided by 50 plus RP plus 50 is equal to 50 RP over 50 plus RP minus 50. And then you add 50, it gets multiplied, and then you can multiply by 50 plus RP, and you get rid of course, you get rid of this part, and then you solve for RP. I'm not going to show y'all like exactly all of the steps because it's, yeah, I hope y'all can do some, algebra here. But what we get is RP is equal to 10, I think I got like 10.03 something ohms, which is close to the answer of 10 ohms. So that's how you do this, this, problem, this TDR problem. You have to know where the TDR lies so that we can have the resistance, the equivalent, or Thevenin, if you want to think about it, the equivalent resistance as seen by the source. Now, I guess it isn't Thevenin because obviously you don't have a voltage source in series with the resistance. Anyways, that's how you would do it using a bounce diagram. But yeah, I mean, hopefully this helped y'all. It might have made it a little more confusing, but he didn't ever go over this. It was never a practice. It was never a homework problem. I don't see him putting this on here, but it's still in the bank. He could definitely do it. But yeah, hopefully it helped. I try to make this quick because my videos have been longer, but thanks for joining.